Hi, how are you doing?
Hello.
Good. All right. So today we're going to look at self-induced voltage. Self-induced voltage. Now, suppose you have a solenoid like this, a coil. Another name for a solenoid is an inductor. So an inductor is just a coil. An inductor, this is just a coil, okay? Is a coil. Now, suppose this solenoid is carrying a current, okay? It's going to produce magnetic field of its own because of the current, right? So you have magnetic field going this way, okay? So the current is going this way, then the field is going to go this way, okay, like this, okay? So its own magnetic field is crossing the coils, right? So there's going to be flux due to its own magnetic field. Because of that, this flux is called self-induced flux, okay? So this flux over here, now the magnetic field of the solenoid or the inductor is crossing the solenoid itself. The solenoid itself. That means there will be flux crossing the solenoid due to the magnetic field, right? This implies there is flux due to its own field. There is flux due to its own field. Its own field. Now you see, let's say n is the number of turns. So the total flux would be n times the flux per unit turn, right? And the flux per unit turn, let's say the area of this one is A, will be the magnetic field times the area, right? You got magnetic field over here. So the flux per unit turn would be the magnetic field times area. The area and the magnetic field are approximately parallel over here, all right? So the total flux crossing it would be this one. Number of turns times magnetic field times the area of the coil, okay? So this is the total flux crossing it. But you know that the magnetic field is actually given by mu naught, number of turns per length times current. You remember that? So you see, this flux over will be N times this one, mu naught N over L times current, okay? Now you see also are constants, number of turns, mu naught and L, they're constant. So it follows that this flux over here is actually proportional to the current. So the flux crossing the solenoid itself is proportional to the current. Now, the constant proportionality between the flux and the current is called the inductance of the inductor, okay? So this tells you that the flux, let's call it self-induced flux. This is self-induced flux, let's refer it over here. The self-induced flux is proportional to the current, okay? So self-induced flux, is proportional to the current. Proportional to the current, okay? And the constant proportionality between the flux and the current is called the inductance of the coil, okay? The constant of proportionality between the flux and the current, is called the inductance of the coil. It's called the inductance of the coil, and we're going to use L to represent it, okay? So we have flux, self-induced flux is proportional to the current. That implies the ratio between the self-induced flux and the current is a constant, okay? And that constant is denoted by L, which is inductance. Okay, so we have the following relationship. The flux, the self-induced flux, is equal to the inductance of the coil times the current. Okay, so so far we've seen two devices. You remember, we've seen the resistor. Resistor is characterized by the fact that the potential difference across the resistor is proportional to the current. We've seen a capacitor. A capacitor is characterized by the fact that the charge accumulated is directly proportional to the potential difference in the plates. So this is the other device. These are the three popular devices in electronics: resistor, capacitor, inductor. And this one is characterized by the fact that the flux due to its own current crossing the coil is proportional to the current. Okay, so this is another important circuit element in electronics. All right, now if somehow you're able to change the current, the flux will be changing. Okay, when the flux changes from Faraday's law, there will be an induced voltage. We call that voltage self-induced voltage, okay? So if the current in the coil changes, there will be an induced voltage due to its own current, and that's called self-induced voltage, okay? So let's look at self-induced voltage. Self-induced voltage, I'm going to use E self-represented, okay? Now, what's Faraday's law? Faraday's law is the induced voltage is a negative rate of the derivative of flux with respect to time, right? So in this case, the self-induced voltage would be the negative of the derivative of the self-induced voltage with respect to time, okay? But we just said that the self-induced voltage is inductance times the current, right? So the self-induced voltage, its own current, is negative the derivative of the inductance times the current, and so you get the following current. So the self-induced voltage of an inductor is given by negative L, the derivative of the current with respect to time, okay? So the voltage induced on itself due to its own changing current is given by the following formula. That is the negative of inductance times the rate of change of the current, okay? By the way, unit of inductance is called Henry. Unit of inductance is called Henry, and we're going to abbreviate it by capital H, okay? So this is the formula for self-induced voltage. It's proportional to the rate of change of current, and the constant proportionality between the self-induced voltage and the current is called the inductance of the coil. Now, this inductance over here is only a function of the geometry of the coil. So you can get an expression for it very easily, okay? So let's now obtain inductance of a solenoid, okay? Let's obtain inductance of a solenoid. Inductance of a solenoid, okay? So remember, we have the following formula: self equals L times I, or you can say simply the inductance is self-induced flux per unit current, okay? So this self-induced flux is N times the flux per unit turn, right? And that flux per turn is simply the magnetic field times the area, if you assume the area and the magnetic field are parallel, okay? So you've got the field going this way, the area going this way, they're parallel. Cosine of 0 is 1. We can represent the flux by magnetic field times the area, okay? And if you remember, B is mu naught, number of turns of the coil divided by the length times the current. So the flux per turn is the magnetic field, which is this one, times L, divided by, times the current, times the area. If it is circular and the radius is R, like this over here, this is R, then we can represent the area by pi r squared, okay? So we have area also equals pi r squared. So instead of A, I'm going to put pi r squared over here, okay? So the total flux, phi self, is simply N times this one. So you've got mu naught N squared times pi r squared divided by L times the current, okay? So this is the self-induced flux. And the inductance is simply self-induced flux divided by the current. Okay, so you divide by the current, you simply get this one, mu naught n squared pi r squared times L. Okay, so this is an expression for the inductance of the coil. Okay, so you see it depends only on the geometry of the coil. You got the radius over here, you got the length solenoid, the number of turns. That's it. It depends only on the geometry of the coil. So it is a constant. All right. So this gives you the inductance of the coil. You remember for a capacitor, we have a similar expression. If you got a power plate capacitor, for example, I don't know if you remember, we have this formula for the capacitance. It's simply a function of the geometry. In this case also, the inductance depends only on the geometry of the coil. Okay. All right, let's look at an example. Suppose the current in the solenoid, let's say, suppose the current in a solenoid, let's say the number of turns is 100 turns. Let's say the length is maybe 10 centimeter, okay, and radius, let's say, is also, let's say 2 centimeters, okay. Varies with time, let's say according to the following equation. Let's say the current is, let's say 4 amps, and then you have sine maybe 60 times time, okay? So the question is, obtain expression for the self-induced EMF, okay? Obtain an expression for the self-induced EMF, okay? Now, the self-induced EMF, as you've seen before, is negative L times the derivative of the current, okay? Or you can just say the negative of the derivative of self with respect to time, okay? And the flux, of course, is number of turns times the magnetic field, which is mu naught n I divided by L, that's the magnetic field. And then you've got the area, pi r squared, okay? This is the self-induced flux. And so the induced flux is, we got this constant over here, n squared mu naught over L times pi r squared, and then times the derivative of the current. Okay, that's it. And this is our current over here. So just put over here. Okay, so we have n squared mu naught pi r squared divided by L, and the derivative of this current over here, 4 times the sine of 60t. All right, so that's it. So I don't know if I should put the numbers, but this would be n squared would be 100 squared. Number of turns is 100 squared. And then of course we have mu naught, which is 4 pi times 10 to the power of -7. This is our mu naught. And the radius is how much? 2 centimeters. That's 0.02 squared. So you've got pi, and then you've got 0.02 squared for the radius, divided by the length, 0.1. How about the derivative of this? This would be 4 times 60, 240, right? The derivative of this one. So it'll be 240 times cosine of 60t. So it will be 240 times cosine of 60t. So this is how the, well, I think I forgot the negative. There's a negative over here. The derivative, there's a negative over here. Negative, all right. So that's how the voltage across the coil is going to change. All right. Now, most of the time we're going to deal with average induced voltage. So let's obtain an expression for average self-induced voltage. Average self-induced voltage. Induced voltage. Okay. So what do you do to get average? Well, is self average would be you're going to integrate it, the self-induced voltage, which is negative L di by dt, integrate this with respect to time. You take it, let's say, from t to t plus delta t. You calculate the area and then divide by the base, delta t. All right. So this is simply, you got negative L out, okay? And this is the integral of di, okay, over delta t, all right? And the integral of di is simply delta I. So you get negative, or let's say this goes from I to I final, you get negative L I final minus I initial divided by delta t, okay? So the average self-induced voltage, self-voltage is simply negative L delta I by delta t, okay? So if you're interested in the average, all in is the initial current and the final current and the time taken for that change, and that'll give you the self-induced voltage, all right? Uh, Example, let's say the current in a solenoid, the current in a solenoid, let's say increase it from, let's say 2 amps to 12 amps, let's say in 0.5 seconds. The question is calculate the average induced self-induced voltage. Calculate the average self-induced voltage. Induced voltage, okay? So all we have is, all we need is the initial current, which is 2 amps. We have the final current, which is 12 amps. Of course, we're going to need the inductance too. Let's say maybe this is maybe 3 millihenry, okay? And then of course, delta t is 0.5 seconds, right? So the average self-induced voltage will be negative L, I final minus I initial divided by delta t. Okay, so it'll be negative 3 times 10 to the power negative 3. And then you've got 12 minus 2 divided by 0.5. All right, so that would be the average induced voltage during this time interval. All right. Next, we're going to look at the magnetic energy stored by an inductor. Okay, you remember in the case of capacitor, the energy stored by the capacitor was electrical energy. In this case, the field we have inside the solenoid is a magnetic field. So we have a magnetic energy due to the magnetic field in the solenoid. Okay, so let's look at the magnetic energy stored by a solenoid. Stored by a solenoid. Okay, now suppose you have a coil connected to a source. Okay, you have this coil over here connected to the source. Now, as this source pushes the current, the induced EMF is going to push against it. Okay, so this is trying to build the energy, but the induced EMF is going to oppose, just like a spring. If you've got a spring over here, if you try to compress it, the spring will push against you. Okay, so the work done by the external force over here, let's say trying to push the spring over here, this is external over here, but the spring pushes back. This is a positive spring over here, okay? So it's this external force that's storing the energy in spring, but that external force has to do work against the force of the spring. The same thing over here. In the you remember Lenz's rule, the direction of the induced current in such is opposite the cause. So when the source tries to build the energy over here, let's say it increases the magnetic field, this is going opposite. So the work done by the self-induced EMF is the negative of the work done by the external force. Okay, so let's say this source over here is trying to push its charge dq through the coil over here. Remember, formula for work is charge times potential difference, right? So the work done by the self-induced EMF would be dq times the potential difference, or EMF, E self, okay? So this is the amount of work that this would do to oppose it, okay? You can charge dq over here. This is the self-induced EMF. So this is like the work done by the spring to oppose it. But the energy being built by the external force, by this force building charge over here. So you can say that the work done by the external force is the negative of this one. It's going to oppose it, okay? E self like this, all right? But what is E self? We know that this is negative L di by dt, right? So this work done by the external force to energize the inductor, you've got negative dq and then negative L di by dt. Okay, so the negative goes away. You've got the work done by the external force to increase the energy of the inductor will simply be dq times L di by dt. Okay, so this is the amount of work the external force has to do in order to increase the energy of the inductor, right? Now let's move this around. We've got dq by dt over here, and then we've got L di over here. What does this equal to? dq by dt, or the rate of flow of charge.
Current.
Current, okay? So we have this work done by the external force to push the charge against the induced voltage is current times inductance times di, okay? Now, the total energy stored as the current increases from 0 to I, we simply integrate, okay? So the total work done by the external force, which is basically the amount of energy stored in the inductor, you simply integrate. Let's say the current increases from 0 to I, and then you've got Li di. Okay, so you see, let me prime over here. Now L is a constant, so this is L I prime squared over 2 going from 0 to I. Okay, so the magnetic energy stored in the inductor when the current increases from 0 to I is simply half L I squared. Okay, so this is the formula for the magnetic energy stored by a solenoid when the current in the solenoid is I. Okay, so this is a formula for the energy stored by the magnetic field. Half times the inductance of the coil times the current squared. Okay, you remember the formula for the energy stored by a capacitor? It was half charge squared divided by 2c. Remember that? That's energy stored by a capacitor. That energy is stored by electric field due to the separation of positive and negative charge. This is energy stored due to the flow of current in the solenoid. Okay, you'll have this much energy stored. You've got a current I over here. Okay, so this is a formula for the magnetic energy stored by an inductor or by solenoid. Okay. Now, if you remember, when we talk about capacitors, we talked about the electrical energy density. Do you remember that? Which is half epsilon times electric field squared. Do you remember this formula? The electrical energy density between the plates of a capacitor. And we said that even though that was derived for a capacitor, is actually true in any case. At any point where the electric field is E, the density of electrical energy at that point is given by this formula, is proportional to the electric field squared. Okay. Now we're going to look at the same thing for the magnetic energy density. So let's look at magnetic energy density. Magnetic energy density. That is energy per unit volume. Magnetic energy density. Okay. So let me use the following formula for that one, magnetic energy density. So this is simply the magnetic energy stored by the solenoid divided by the volume of the solenoid, right? The volume, V is volume of the solenoid. And what's the volume? The volume is the length solenoid times its cross-sectional area, right? So the volume is, you take the length solenoid, you multiply by the area of the base, pi r squared, that gives you the volume, okay? So the energy density due to the magnetic field is the energy, which is this one, half Li squared. This is the energy stored by the solenoid in the current as I. And then you divide that by the volume of the solenoid. That'll give you the density of the magnetic energy stored by the solenoid. Okay, so now we're just going to substitute I in terms of magnetic field. We have also an expression for L for a solenoid. Let me rewrite it. So let me copy that. So this is the inductance of a solenoid, remember that? So let me put L over here. L is mu naught n squared pi r squared divided by L, okay? So this is the inductance of a solenoid. And also, of course, we know current is mu naught, number of turns divided by length times the current, right? So that tells you, oh, this is a magnetic field. I'm trying to express this in terms of magnetic field. So the current is B times L divided by mu naught N, okay? So the current in terms of magnetic field is length times the magnetic field divided by mu naught N, okay? So all we're going to do is I'm going to put this for L, I'm going to put this for I, and then we'll simplify it, okay? So the energy density, we've got half. We have L over here, which is mu naught N squared. This is mu naught N squared divided by L, I think. And then pi R squared, pi R squared. This is the value for L, okay? And then of course, we have current. Current is this one, LB over mu naught N squared. This is the current, and that's divided by the volume, which is L times pi R squared, okay? So we just have simplified L times pi R squared. All right. So first we see that this cancels out, pi R squared. Do you see that? This cancels out. So we've got half over here. How about L? You've got 1 over L over L, that's going to be L squared. Okay, so you've got 1 over L squared over here. You see that? You've got 1 over L over here. That'll give us L squared. Okay, how about N squared? Well, N squared, we still have it over here, N squared. And then we have mu naught, this one over here. Okay, and then we're going to square this one, L squared B squared over mu naught squared N squared. Okay, so this is that L squared goes with L squared, N squared goes with N squared. Okay, all we have is 1 over mu naught. This is it. So this magnetic energy density is simply the square of the magnetic field divided by 2 times the magnetic permeability of vacuum. Okay, so this is a formula for the magnetic energy density of a solenoid. Now, even though we have derived it for a solenoid, this is actually true at any point. At any point where the magnetic field is B, this is the magnetic energy density at that point, okay? So this is a very general formula, even though we derived it from a specific example for a solenoid. So this is generally true at any point where the magnetic field is B, then the magnetic energy density is given by this field, okay? And if you remember, the equivalent for electric field was epsilon over 2 E squared, okay? This was the electrical energy density, and this is magnetic energy density, okay? Now, this is the equivalent of potential energy. This is the equivalent of kinetic energy. Remember, this is related with current. Current is motion of charge, okay? So when you compare with the spring, the potential energy of the spring is related with this electric field. Remember, electric field is energy when the molecules extend and compress, right? So that is potential energy. When you pull the positive and negative end for molecule, that is the potential energy stored in the molecule. So this is the equivalent of potential energy. This one is due to motion, okay? So the equivalent of this is kinetic energy, okay? So in electromagnetic energy, this is the equivalent of kinetic energy. It's current, which is motion of charges, and this is the equivalent of potential energy, right? Okay, now we're going to look at a circuit, a resistor, and an inductor connected to a DC source. A resistor, and an inductor connected to a DC source, source. Now we have the following circuit. We have this is the source, like a battery, and then we have a resistor over here with resistance R, and then we have a coil. By the way, this is a symbol of an inductor or coil, okay? And that's identified by its inductance L. So we want to look at this circuit, okay? So let's say we've got current flowing over here. Now we're going to apply Kirchhoff's rule. Let's say the EMF of this one is E, okay? So as you go from negative positive, the EMF of this one is positive. When you go in the direction of the current, the potential difference minus I times R. And this one we just learned today, the self-induced EMF is L di by dt, okay? Equal to 0. It's simply Kirchhoff's loop rule. Okay, we just add up all the voltages and add them together. So we have solved this differential equation. Well, the first thing we need to try to do is to separate the variables. Okay, so let's take this to the other side. So we've got negative L di by dt equals IR minus E, or we have di by dt, okay, equals the negative flip this one minus IR and divide by L. Okay, so now you see if I bring this to this side and the term this side, that will separate the variables and then I can do the integral. Okay, so we can write this one as di over this one, E minus IR equals 1 over L times dt. Okay, so I've separated the time integration and the current integration. Now I can solve the problem. Okay, so we're just going to integrate both sides. So we have the integral of di over EMF minus IR equals the integral of 1 over L dt. Okay, now the current starts from 0 and then builds up to a current I. Okay, so this goes from 0 to t. The current will go from 0 to I as a function of t. Okay, so we want to get an expression for the current as a function of time. All right, so this one, of course, is simply t divided by L. Okay, so let's do this side. So we're going to use measure of substitution. Let's say let U equals EMF minus IR. Okay, so that gives me du equals, this is a constant, this is simply negative R di. Okay, and then U at t equals 0, or U at I equals 0, I'm talking about this limit over here, is simply E, right? When you put 0 over here, you get E. How about U at an arbitrary I, you simply get E minus I as a function of time times R. Okay, so we can modify this integral as follows. This goes from EMF E and then E minus IR over here. Okay, and then di over here is negative du over R, right? So you've got negative du over R over here for di. And then, of course, this is E minus R is U. So you've got 1 over U over here. Okay, that equals T over L. Okay, so let's take this constant negative 1 over R. So this integral from EMF E to EMF minus IR is going to be du over U, and this will be negative R over L T. All right, and what's this integral? The integral of 1 over U is ln U, right? Can you read it? This is the integral of 1 over U is ln U. So you've got ln U going from E to E minus IR equals negative R L over T. Okay, and that will give me the ln of E minus IR over E. E minus IR over E equals negative R over L T. All right, and then I'm going to change this to an exponential function. Okay, so that gives me E minus IR over EMF equals E to the power of negative R over L T. All right, So you've got the EMF minus the current times the resistance is EMF times e to the power of negative R over L T. Okay. Remember, we're trying to solve for the current. So IR equals EMF minus EMF E negative R over LT. Okay. And then we can factor this out. We've got EMF and then 1 minus E negative R over LT. Okay. And we divide by R, we get the current as a function of time is EMF divided by the resistance and then 1 minus E negative resistance divided by inductance times time. Okay. So this is how the current varies as a function of time. Okay, now let's plot this graph approximately. First of all, this number is very important because it controls how fast it goes to the maximum value. Okay, R over L, so it's called time constant. The expression R over L is called the time constant of the circuit. The reason is it's a number that controls how fast it goes to a steady state. Does it go slow? Does it go fast? If it's a large number, it goes to a steady state very fast. If it is a small number, it goes very slowly to a steady state. So it's very important for designers. It's called the time constant of the circuit. All right. So let's look at the properties for 0 and infinity so that we can plot the graph approximately. So what's I at t equals 0? You see, put 0, this becomes 1. 1 minus 1, 0. So I at t equals 0 is 0. Actually, we started by assuming it's 0. And then at infinity, I at t equals infinity. You see this negative, so at infinity is going to be 0. Okay? We just have this one over here. So this one is E over R. Okay? So now with this extreme values, we can plot the graph of the current. All right? So you've got, let's say this axis is the current as a function of time. And this one is, let's say, time. So at t equals 0, that comes over here. And then it approaches this value as t goes to infinity. And that value is E over R, EMF divided by the resistance. So it will approach this line asymptotically. Okay, it will go like this. So how fast it approaches this line depends on the time constant R over L. Okay, so it's a very large value, it's going to go like this. If it's a very small value, it's going to go very slowly over here. And that's why it's an important number for circuit designers. All right, so this is the current in the circuit. Okay, if you're interested in voltage across the inductor, it's simply current times resistance. Okay, and that will be resistance times what we have over here, which is E over R times E over R, and then you got 1 minus E negative R over L T. Okay, so the voltage across the resistor will simply be EMF 1 minus E negative R over L T. Okay. If you're interested in the self-induced EMF, that's negative L di by dt, right? That's going to be negative L, the derivative of this one, of the current, which is E over R, and then we've got 1 minus E negative R over L T. Okay, so you've got negative L. The dirt, this one is 0. So these two negatives are going to go away, but we're going to have a negative from here. So you've got R over L over here. This we have R over L coming out over here. And this would be E, well, this E over R over here, I'm sorry. Well, number again. So you've got negative L, E over R, and when you take the derivative over here, you can get negative R over L like this, and then E negative R over L T. Okay, so you've got positive over here, so this is going to be negative. You got resistance going away. You got this one going away. So it's just the negative of EMF. So this self-induced EMF in the inductor is negative the EMF E negative R over LT. Okay, so this gives you the self-induced EMF in the circuit. All right, so this one at 0 is going to be negative E. Okay, but at infinity it goes to 0. Okay, so this will start negative E over here, and then it goes to 0. It will be like this, the self-induced EMF. All right. Okay. Now we're going to look at mutual inductance. Mutual inductance. Now, so far we've seen the voltage induced on a coil or inductor by its own current, okay? But now we're going to look at a case where that voltage induced by another coil nearby, okay? Suppose you have these two coils, okay? Suppose you have these two coils over here. Let's say this is coil one over here. And then we have another coil over here. Let's call this coil 2, okay? Now, this one, because of its current, is going to produce magnetic field. But that magnetic field is going to cross this coil over here, okay? So we have flux induced on this coil due to coil 1. Do you see that? We're going to have flux induced on this coil due to the magnetic field or the current in this coil, okay? So let's say the flux per unit turn induced on 2 by 1, okay? This would be, we're looking at the flux crossing this one, but that one is due to this magnetic field, okay? So it'll be magnetic field due to 2, but times the area of this one, okay? That's called A1. So this is the flux per unit turn in this case. Do you see that? The magnetic field, no, I should say, no, this is 1 over here. The magnetic field is coil 1 times the area in coil 2. You see that? You've got flux due to this magnetic field on coil 2. So we're looking for the flux on coil 2 due to the current in coil 1. Okay? So what is B1? B1 would be mu naught, number of turns of 1 divided by the length. Let's say they have the same length times I1. Okay? But then you have the area of the second coil. Okay? So what we see over here, this flux crossing this one over here is proportional to the current over here. All right? So what we have is, well, the total flux, you can multiply it by N, but generally, well, we have the total flux would be N times flux per turn to 1, okay? So this is the total flux on 2 by 1. So you can see over here, all these are constants. The number of turns, the area, and so on are constants. So we see that the flux on 2 by 1 is actually proportional to the current in 1. Okay, so the flux on 2 by 1 is proportional to the current in I1. Okay, so that means the ratio between the flux on 2 by 1 to the current in 1 is a constant. Okay, so what we have is the flux on 2 by coil 1 is proportional to the current in 1. Okay, that means this flux by 2 on 1 divided by I1 is a constant. Okay, this constant is called the mutual inductance of the coils. This is called the mutual inductance of the coils. Okay, now we have two coils involved. So this is the mutual inductance of the coil, and this will be denoted by the mutual inductance of coil 2 with respect to 1. Okay, now there's current in coil 1. You could do the same thing for 1. You can say M12 is also phi 12 divided by I2. Okay, but it can be shown that these are actually equal. So we're just going to say this is a property of geometry with two coils. So it's going to be a constant. So M21 equals M12, just say M over here. So we have the total flux of 2 by 1 is equal to the mutual inductance times the current in 1. Okay? And this constant proportionality is called the mutual inductance of the two coils. This capital M over here is the mutual inductance of the coils. Okay? Now let's look at the voltage induced by coil 2 on coil 1. On coil 2 by coil 1. Let's look at voltage or EMF induced on coil 2 by coil 1. Okay? So looking at E2 over here. This will be the negative of the derivative of the flux on 2 by 1 with respect to time, right? From Faraday's law. But this one is mutual inductance times the current in 1, okay? So we have, this is negative, the derivative, mutual inductance times the current in 1, all right? So M is a constant, so we have a formula. So the voltage induced on coil 2 by 1 is negative M times the derivative of the current on coil 1, okay? You can do the same thing for E1. E1 would be negative M times the derivative of I2 with respect to time, okay? So in this case, we're talking about the geometry of two coils, and the constant proportionality between the flux and the induced EMF is called the mutual inductance of the coils, okay? So now let's look at an example of obtaining the mutual inductance of two solenoids, okay? Let's look at mutual inductance let's say, of two concentric solenoids, okay? Let's say of the same length to make the discussion easier, of the same length. Okay, so we have two solenoids over here. We have one solenoid over here, and then we have a bigger one. We have a bigger one over here. Okay, so this will be, so we have another one over here. Okay, so let's say this is my coil 1. Let's say this is my coil 2. Okay, so let's look at the flux on 1 due to 2. Okay, so the flux on 1 due to 2. Now we're looking at the flux crossing this one, okay? So we're going to multiply by the number of turns 1 and then the cross-sectional area of this one, A1, okay? But the magnetic field, D2, right? So that's B2, okay? So that is the flux crossing 1 due to the current in 1, okay? And what's B2? Well, B2 is mu naught N2 divided by the length times I2. Okay, so the flux crossing coil 1, the flux crossing coil 1 due to coil 2 is given by the following formula. You've got N1A1, and then we have mu naught N2 divided by the length times the current in 2. Okay, so what is the mutual inductance? Mutual inductance is the ratio between the flux on 1 by 2 divided by the current in 2. This is the definition of mutual inductance, right? So again, you divide this one by I2, okay? We got N1, A1, mu naught, N2 over L, and then you got I2 over, so I2 goes away, okay? So this is the mutual inductance of the two coils. We've got mu naught, we've got a product of the two coils, the number of turns, and then divide by the length. And then for the area, if you want, you can use pi r1 square, assuming cross-section, pi r1 square, assuming the cross-sectional area is a circle. Okay. So this would be the mutual inductance of the two coils. It's purely a function of the geometry of the two coils. Okay, you got the number of turns, you got the radius of 1. All right, so that's how we obtain the mutual inductance of two coils. All right, now suppose we have the same two coils over here. It's 3, well, I should do it. Suppose, let's say I1 is maybe 2 sine 60t, let's say, and I2 is, let's say, 4 times sine of 60t, like this. Okay. Well, let's just substituting these numbers. I don't know if I should go through it. But the main thing is you'll obtain the inductance, and then for the induced EMF, we'll just say negative M di1 by dt. So I don't know if I should go through it. You will calculate M using this form over here, and then do the derivative of the current. I think let's proceed. It's just tedious calculation. All right. Now we're going to look at LC circuit. That is a charged capacitor connected to an inductor. A charged capacitor connected to an inductor. Connected to an inductor. Okay, so in this case, what it is, first you charge the capacitor like this, and then you connect it to an inductor. So let's say the capacitance with the capacitor is C, and the inductance one is L. So we want to study the property of this circuit. Okay, it's a very interesting property. Okay, so from Kirchhoff's law, we're going to have a source over here. We're just going to have, for the capacitor, we have negative Q over C, the potential difference. And for this one, we just learned today, it's L times di by dt. All right, equals 0. That's applying Kirchhoff's law. So you go this way, negative L di by dt, negative L di by dt equals 0. Okay, so basically the negative goes away. So we've got L di by dt plus Q over C equals 0. So this is our equation. All right. Now we have di by dt equals plus, so let's make the quotient this one, LC equals 0. So this is our differential equation, okay? But we have I and Q, okay? What does I equals in terms of charge? How does current relate in terms of charge?
Is the derivative charge?
Derivative. I is dq by dt, okay? So we're going to put dq by dt, this is going to be second derivative, okay? So we have the second derivative of q with respect to time plus 1 over LC times Q equals 0. Okay? So you've got a differential equation where the second derivative is proportional to the charge itself. Have you ever seen this differential equation before? We solved it last semester. You remember the motion of a spring? Remember that? Well, for a spring, you would say mass times acceleration, d squared by dx squared, plus kx equals 0. Remember this differential equation? Okay, take this one over here. This is m over here. This is second derivative proportional to the displacement. This is the motion of an object attached to a spring. What happens? It goes forever up and down. Okay, you remember the solution for this one? What was the solution? The solution was a cosine as a function of time. Okay. Well, this is second order differential equation, okay? So you have to come up with two independent solutions, and the general solution is a linear combination of those two solutions. So in this case, both cosine and sine satisfy this differential equation, and the general solution will be a linear combination of sine and cosine, okay? So we did this in detail last semester during spring, so I just want to write the solution in this case, Okay, so the general solution for this one would be q as a function of time. You've got, let's say, a constant over here, and then cosine of it's going to be 1 over square root of LCT minus another constant over here. This is the general solution. Okay, it's a cosine function. It just goes up and down, just like for a spring. Okay, so this C1 and C2 are to be determined from initial conditions. Okay, so what do we know? Well, we have initial charge. Let's say the initial charge over here at t equals 0, we start with this charge, Q max. Okay, and then of course the current is 0, so you can say dq by dt at t equals 0 is also 0. Okay, so we have these two initial conditions. We start with a certain amount of charge, so let's say q at t equals 0 equals the initial charge, which can be the maximum. Okay, and then the initial current is 0 initially, so you can say t equals 0 also equals 0. Okay, so with this initial conditions, we can simplify, we can find values for these two constants. Okay, let's start with the first one. Q at equals 0 at equals 0 equals C1 cosine of, that's negative C2 over here. Okay, that equals Q max. Okay, so you've got C times cosine negative C2, or this is an even function. We can put C2 over here, equals Q max. Okay, how about the other one? The derivative dq by dt of this expression is negative C1 over 1 square root of LC over here, and then sine of C2 equals 0. Okay, now there are two ways this can be satisfied, either C1 equals 0, C2 equals 0, but if you say C1 equals 0, we're going to say Q max equals 0, so that's not going to, so we're going to say this implies C2 equals 0. Okay, C2 equals 0. C1 equals 0 means this is 0 over here, so we don't want that. All right, so you got C2 equals 0 from here. Now let's go over here. When you put 0 over here, what do you get? Just C1. Okay, so we have C2 equals 0 over here, and then we go to the expression Q at t equals 0 equals C1 cosine of C2 equals 0. This implies C1 cosine of 0. Oh, this is Q max. I'm sorry. This is Q max. This is Q max over here. So it follows C1 is Q max. Okay. Okay. So with this initial conditions, the general solution is Q of t equals the initial charge, and then you've got cosine 1 over square root of LC times t. Okay. So what does this expression represent? This is the coefficient of time. Do you know? Is it the period, frequency, angular frequency? What is it? Angular omega t. Okay.
Yeah.
So you can say let 1 over square root of LC be omega naught. Okay. So this is just angular frequency of the motion. Angular frequency. Okay. Well, the frequency is 2 pi. We have omega equals 2 pi f. You remember that? So the frequency is omega over 2 pi. Okay. And so with this, you would say 2 pi f naught equals 1 over square root of LC. So the frequency is 1 over 2 pi then the square root of 1 over LC. Okay, so the frequency. And of course, the period for this one will be 1 over f naught. Okay, 1 over f naught. And that will be 2 pi square root of LC. Okay, so this is basically a cosine function. Okay, So the graph looks like this. We have a maximum value, which is Q max, right? So it's a cosine function. It's going to go like this. Go like this. All right. And this distance over here is T naught, the period of the motion. Okay. And that's of course 1 over F naught. All right. Okay. So this is the general solution of the differential equation. Let me put that in the box over here. So you've got Q of T equals the maximum charge times cosine of, I'll just say omega naught T over here, okay? Omega naught is 1 over the square root of LC, okay? So this is how the charge varies as a function of time. How about current? The current is the derivative of the charge, right? So you will have, this will be negative Q max omega naught times the sine of omega naught, okay? You remember omega is 1 square LC, so this is Q max square root of LC times the sine of omega naught T, or put maybe 1 over square LC times T, okay? So this would be the current as a function of time. Current as a function of time, all right? So now you see this circuit will never stop. You see cosine never stops. This is a charge in the capacitor, changes from positive to negative forever. If you've got a spring, you let it go, what happens? Unless there is friction, it goes forever. That's what's happening over here. You see, the charge will start from maximum, it will go to negative, goes up, down. It never stops forever, just like a spring. There's no friction, okay? So that's what's happening over here. So let's look at the energy of this circuit. That's the important property of this kind of circuit, okay? So let's look at the energy of an LC circuit. Energy of an LC. You remember for a spring, its mechanical energy is conserved. Remember that? That the sum of the kinetic energy and potential energy is conserved. This has very similar property with a spring. So you remember for a spring over here, the mechanical energy, which is the kinetic energy plus the potential energy, half kx squared, is a constant. You remember that? Because it is a conservative force. All right. So you can calculate this constant by its value at equals 0, right? Let's say you start from maximum value and let it go. Let's say x at t equals 0 is a, and at t equals 0, the speed is 0, okay? So you put 0 over here, you put a over here, which is amplitude over here. Then you have the following formula: half m v squared plus half k x squared equals half k a squared. This is a question for spring. At any point, if you add up the kinetic energy and the potential energy of the spring, you get its initial potential energy that is extended by this much. Let it go. This is initial potential energy. But then what happens is it's just the energy alternates between kinetic and potential of the spring, vibrates back and forth. Okay. Now let's see, this is a very similar situation. So let's start from the differential equation for this circuit. Remember, it was negative Q over C, this one over here, negative LdI by dt equals 0. This is the differential equation that governs this circuit. Okay. So we have negative Q over C minus L di by dt equals 0, okay? Or we can multiply this by negative, get Q over C plus L di by dt equals 0, okay? So let's multiply this equation by dq, okay? dq over here, and this times 0, all right? So what do we have? We have 1 over C q dq for this one. This one, you got dq, I'm going to put the dt over here. So you've got dq over dt, I just move this dt over here, okay? L di equals 0, right? What is this one? This one is current, right?
I.
But dq by dt is the current in the circuit, okay? So we have the following. Let me put this one first. First, we have L IDI, and then we have 1 over C Q dq is a constant. Okay, now we're going to integrate. Not a constant, this is 0 right now, but we integrate is going to be a constant with indefinite integral. Okay, so let's integrate this. What do we get? Half Li squared over 2 for this one, right? So we get the following: half L I squared. How about this one? Q squared over 2c, and then it's indefinite integral to the constant. Okay, that's the equation we get. But do you remember what does this expression represent? We just did it today. What does half Li squared represent? This is the magnetic energy stored in the coil, in the inductor. Okay, and what does this represent?
Electrical energy.
Electrical energy stored in the capacitor. So what the saying is the sum of the energy stored in the magnetic energy stored in the inductor and the electrical energy stored in the capacitor is a constant. But you know the current and the charge are changing. So what's happening is just an interchange between magnetic and electric energy. What's happening is simply an interchange between electrical and magnetic energy. You see in a spring, what happens? You start with maximum potential energy and then the speed increases. Okay, all that takes place is an interchange between velocity and displacement, or kinetic energy and potential energy. In this case, what happens is all that takes place as this vibration takes place is an interchange between magnetic energy and electrical energy. Okay, so if it's a constant, it should be equal to the initial energy, right? So let's look at the circuit over here, the initial circuit over here. To start with, we have this energy over here. The initial energy of this one is Q max squared divided by 2C, right? The initial energy before the circuit is turned on. And there's nothing over here. There's no current, there is no magnetic energy over here. So you've got this energy plus 0 magnetic energy. This is the initial energy you have. But the energy is a constant. So what's going to happen is electric energy will be converted to magnetic energy will be converted to electrical energy, but it's always equal to this value. Okay? So this constant actually equals Q max squared over 2C. So this constant over here, let's say energy at T equals 0, at T equals 0 equals charge squared divided by 2C. All right, so we have the following formula: half L I squared, magnetic energy stored in the inductor when the current is I, and then plus half Q squared over C, electrical energy stored in the capacitor when the charge Q equals to the initial charge, which is Q max squared divided by 2C. Okay, so we have this relationship between the magnetic energy and the electrical energy. Now compare this with spring. For a spring, we have the following question. The kinetic energy is half m speed squared. The potential energy is half k x squared, okay? And the initial energy when the spring is extended by amplitude a is half k a squared. This is symmetry. So for electromagnetic energy, this is the equivalent of kinetic energy. So magnetic field is what gives the electromagnetic energy is kinetic energy, because this is current. Current is motion of charge, okay? So this corresponds to kinetic energy, and this corresponds to potential energy, okay? So the electrical energy represents potential energy. The magnetic energy represents this motion energy. It's very easy to see. Current is flow of charge. So this is obviously motion energy. And this one, this energy over here is the suppression of charges. So it's obviously potential energy. Okay, so this is the equivalence between the motion of a spring and this characteristics of the LC circuit. All right. Okay. And now we're going to look at another circuit. Now we're going to look at three of them: resistor, inductor, and capacitor connected to a DC source. Okay. A resistor, an inductor, and a capacitor, and a capacitor connected to a DC source, connected to a DC source. Okay, so we have the following. We have a DC source over here, and then it's connected to a resistor identified by its resistance R. You've got an inductor identified by this inductance L, and then you have a capacitor identified by its capacitance C. Okay, so this is the circuit we have. So suppose the EMF of the source is E, so we're going to have a flow of current this way. Okay, so we're going to apply Kirchhoff's law. Okay, if you go in the direction of the current, this will be positive, and then you've got minus I times R for the resistor, minus L di by dt for the inductor, and then minus Q over C for the capacitor. Okay, this should be equal to 0. All right. Okay. So we have current equals dq by dt, right? Current equals dq by dt. So this is going to be dq by dt, is going to be second derivative, right? So that gives you E minus dq by dt times resistance minus L, second derivative of charge with respect to time, and then minus Q over C equals 0. Okay, so as you can see, we have a second order differential equation, but let's rearrange it. So this would be, we have L, let's put the second derivative first, dt squared. So I'm going to multiply the whole thing by negative, and then plus dq by dt plus R times dq by dt. Okay, that is for the resistor over here. And then for this one, plus Q over C plus Q over C equals the EMF E, this one right here, okay? So you've got E over here. So it's a differential equation. But let's standardize it. Let's divide by the coefficient of the second derivative, okay? So that gives us the second derivative of the charge plus R over L, the first derivative of the charge, and then plus 1 over LC times charge equals EMF. Okay. So this is, and it's not homogeneous differential. Do you know the difference between homogeneous and inhomogeneous differential equations? The second order differential equation, but it's not homogeneous. It is homogeneous, this is 0. This is inhomogeneous differential equation because this is not 0. Okay. So to solve an inhomogeneous differential equation, what it is, you express the solution as a sum of the solution of the homogeneous differential equation by assuming this is 0, and then a particular solution, which is the solution of the entire differential equation. Okay, so you can express the solution as follows: Q of t equals the solution of the homogeneous differential equation plus a particular solution of the differential equation. So this could be any solution of this differential equation. Okay, and then If you put this over here, this, remember, this is the solution when this is 0. Okay? So when you put QH over here, this is 0. We're saying this is the solution of the homogeneous differential equation, right? So when you put this expression over here, QH just gives you 0 over here. You just left with QP. Okay? So for QP, this is, we're going to assume QP to be a constant. Okay? We have an easy solution if we assume QP to be a constant. So this becomes 0. This becomes 0. You just have this one. Okay, the derivative will be 0 is a constant. You just have this term over here. So the particular solution would be 1LC times QP equals the EMF. Oh, I didn't divide by L over here. Okay, the E over L over here. Okay, so 1 over LC QP equals this one. So L goes away. You see the particular solution is the EMF E times the capacitance C. Okay, so that's my particular solution. All right, so now all I have to do is find this solution over here. And the general solution will be this solution plus this particular solution. Okay, so for the homogeneous solution, we said this is 0. Okay, and our solution will be, so our solution can be like this: Q of T equals QH plus this one. Okay, where QH is the solution of the homogeneous differential equation, or QC, I mean, where QH, where QH is the solution of the homogeneous differential equation. Homogeneous differential equation. Okay, and that differential equation is this one. We got d squared K by dt squared plus R over L dq by dt plus 1 over LC Q equals 0. Okay, so this is an equation for the homogeneous equation where QH is the solution of that differential equation. Okay, so we have to solve for this one now, but let's rearrange this. Remember this value over here, 1 over LC, represented by omega naught squared. Do you remember? It's called the natural frequency. Now let me remind you something we did in the last chapter last semester. Dampened motion. Do you remember? We have a force proportional to the velocity in addition to the force. We have the following. You have another force which is proportional to the velocity. So we have the following. You've got mass times acceleration dx by dt squared, okay, equals a force proportional to the velocity, or dx by dt, and then a force proportional to the displacement. Okay, this was the damping factor. We have the same situation over here. See, you have a factor proportional to the derivative of the charge. This is this term over here. You see, when you don't have this term, you don't have damping. It keeps oscillating back and forth. But if there's a resistance, such as this one, such as air resistance or water resistance, and so on, then there's going to be damping. Okay, so this is an equation where there's damping proportional to the first derivative of the charge. This over here is the equivalent of this this force, which is proportional to velocity. Okay, you got current is equivalent to velocity, right? So you've got another term over here proportional to the velocity. When this is 0, this is a frequency. We call this one natural frequency. So omega naught is called the natural frequency. It is a frequency when there is no resistance, such as air resistance, water resistance, and when there is no this term. You saw it. If this term is not there, you get a cosine solution that oscillates forever. Okay, all right. So this is omega squared, and then we're going to write this one as 2 beta. Let R over L be 2 beta. Okay, so now let's write it like this. Well, I'm over here. So we got d squared QH by dt squared plus 2 beta, the first derivative, and then plus omega naught squared QH equals 0. Okay, so this is identical to the equation of a damped harmonic motion we wrote last semester in the last chapter. This was our equation. You remember? dx dt squared plus 2 beta dx by dt plus omega naught squared x equals 0. Remember this equation? You've got the term proportional to displacement. You've got another term proportional to the velocity. This was a damping term over here. Okay, so we've done this differential equation in detail last semester when we did damped harmonic motion. So I don't know if I should do it in detail over here. Let's just say there are 3 types of solutions over here. 3 types of solutions. 3 types of solutions depending on the following discriminant. Depending on whether this constant over here, beta squared minus omega squared, is less than 0, greater than 0, or equal to 0. Okay, there are 3 solutions. This is basically the discriminant of a quadratic equation. Okay, if you put a solution in the form e to the power of RT over here, you will get a differential equation. And remember the discriminant of this one? You know the solution of a differential equation? You can say x plus or minus negative b plus or minus square root of b squared minus 4ac. Okay, this is a discriminant of the quadratic equation, right? So if you put 2 beta for this one, you get 2 beta squared minus 4, a is 1, c is omega naught squared. Okay, so you factor out 4, this is proportional to square root of beta squared minus omega naught squared. Okay, so for this quadratic equation, we're going to have 3 different solutions depending on whether this is positive, negative, or 0. Okay, if this is 0, it's a perfect square. If this is negative, you see you're going to have an I over here, complex number, and you can show that the solution is going to be an oscillatory motion. Okay, but if this is positive, you get a damping motion. Okay, so, but as I've said, just put e to the power of RT over here, you will get this the differential equation for this quadratic equation. Okay, and that's how you get this one. Okay, so let's start with the damped solution. The damped solution, let's go number 1. Damped oscillatory solution. Oscillatory solution. For this one, the homogeneous would be a certain constant over here, E, negative beta t, and then we've got cosine of omega t minus a constant phi over here. Okay, this is a general solution. A and phi are constants. And this one, omega over here, is the square root of, remember, well, I should write the condition for this one. The condition for this one is beta squared minus omega squared less than 0. Okay, when this expression under the square is negative, you get a complex number, and that complex number will give you to an oscillatory solution. Okay, so that's the condition for this one. All right, so this one, to make it positive, we're going to put omega squared first. So this is the value of the frequency over here. So this is a general solution for this one. For the homogeneous solution, so the general solution, if you remember, is the homogeneous solution plus the particular solution. Okay, so the homogeneous solution is this one, A, E negative beta t, cosine of omega t minus phi. Phi and A are constants, plus the particular solution. Do you remember the particular solution? QP? It was E times C. You remember over here, this is a particular solution, all right? And the general solution is the sum of these 2 solutions. So this is general solution plus the particular solution, EC, okay? So this is the general solution for this kind of motion. When this discriminant is less than 0, is negative, this is a general solution. And the solution will look something like this. It will start like this, but then it goes to 0 like this, okay? So this is the kind of, for example, if you open a door, you notice sometimes it will go back and forth. When you open a door, you let it go, it goes back and forth and eventually stops, okay? That's that kind of solution over here. Damped oscillation. This amplitude decreases and eventually goes to 0, okay? So this is one kind of solution. The other kind of solution is overdamped solution. Overdamped solution. This happens when this is positive. Beta squared minus omega squared is positive, okay? And that solution is, you see you have two solutions over here. You see over here. So we're gonna have negative beta. Let me just write the solution. So the general solution for this one, for the homogeneous, is going to be a constant E negative, right over here. So QH, that's homogeneous solution, would be C, and you're going to have negative beta plus or minus. So you got the first one, let's say it's plus beta squared minus omega naught squared, okay, T. And then the other, oh, there's E over here, I'm sorry. And then C2, E, and then the other root, negative beta minus square root of beta squared minus omega naught squared, T. Okay, this is a general solution. This has to be determined from initial conditions, okay? And the solution of this one would be like this. It starts over here, but doesn't oscillate, will eventually go to 0, like this, okay? All right. And then the third one is critically damped solution. Critically damped solution. Critically damped solution. Now, this occurs when this is 0. In other words, when the quadratic equation is perfect square, okay? Beta squared minus omega squared equals to 0. This is the condition for this kind of solution. So since a perfect square, you have only one solution, right? Remember the second order differential equation? You need to have two linearly independent solutions to add them together like this, okay? But this one has only one solution. But as you've seen last semester, if E negative beta T is a solution, then T E negative beta T is also solution, is also a solution. All right. So the general solution for this, well, I should add, this is the, well, let me make general this one as a particular solution over here, EC, okay? So this is solution for homogeneous equation, and then you add EC over here, becomes a general solution. And then for this one, it will be C1 E negative beta T plus C2 T E negative beta T, and then plus the particular solution. Okay, so this would be the solution for this differential equation. All right. Now, the only difference between these two, damped and critical damped, is that this one goes much faster to 0. This one just goes to 0 faster. That's the difference. Okay. Critical damped goes much faster to 0 than overdamped solution. All right. So these are three different kinds of solutions for this kind of differential equation. We have underdamped oscillatory motion, driven by a cosine, damped by an exponential function. And then you've got a linear combination of two exponential functions. And then you have a linear combination of an exponential function and a product of t and exponential function, okay? These are the three different solutions we have. But as I've said, we've solved the same kind of differential equations last semester when we did the damped harmonic motion. Okay, so finally, we're going to look at a transformer. Transformers. What do transformers do? Can you tell me? What are transformers used for? When do you use transformer? When you want to increase or decrease voltage, right? That's when you use transformers. If you want to increase your voltage or to decrease your voltage, you can use transformers. So let's see how they work. So what they have is, they have an iron core like this to increase the magnetic field. Okay. When you put an iron core in a magnetic field, you see the magnetic moments of the iron core will line up in the direction of the field and they increase magnetic field. So they usually do that so that they can increase the magnetic field. So we have two coils over here. We've got a coil over here, that's called the primary or coil 1. Okay, so we have an input voltage over here. Okay, let's say the number of turns over here is N1. And then there is another coil over here. Okay, that's where the output, this is the input. It's called the primary coil, if you want. This coil over here, called primary coil. And this one over here, you get the output over here. It's called the secondary coil. Secondary coil over here. Now the main thing is both are processed by the same amount of magnetic field. Okay, the magnetic field throughout over here is the same. So that means the flux per turn over here and the flux per turn over here are equal. Okay, so flux per turn in coil 1, because flux is B times A, right? The magnetic field will be the same throughout for both coils, it will be the same for both coils. And the area, the size of the coil, the same, will be the same. So the flux per turn for this coil is the same as the flux per turn for this coil. All right, that's just called flux per turn, right? How about the total flux over here on the primary coil? The total flux for the primary coil will simply be N1 times flux per turn, right? You multiply N1 times flux per turn. How about the total flux for coil 2? Will be N2 times the flux per turn. All right. Now, let's obtain the voltage induced over here from Faraday's law. The voltage induced in the primary coil is L equals negative N1, the derivative of the flux per turn. Okay, this is E1. How about over here? E2 would be negative derivative of, you got N2 is a constant, and they've got derivative per turn respect to time. Okay, so these two are equal. Now let's do the ratio. A2 over E1. Okay, so that is negative N2, the derivative of the flux per turn respect to time, divided by negative N1, the derivative of flux per turn respect to time. Okay, this goes away. They're the same. What do you get? You got E2, the ratio between the EMFs equals the ratio between the number of turns. All right, you know what that means now? The voltage you get over here, the output, E2 is, you see, N2 over N1, this is one over here, times E1. This is N2 over N1 times E1. So you see, in control how much voltage you get out of here by controlling this ratio. Okay, let's say this is twice than this one, you get twice the voltage. If this is 4 volts and you use 200 turns for N2, 100 turns for this one, you'll get 8 volts. Okay, if this is used to increase the voltage, the transformer is called step-up transformer. If it is used to lower the voltage, it's called step-down transformer. Okay, So that's how transform works. Okay, this is the output over here. This is the output. This is the input over here. And you can control how much you get from the output by just controlling the number of terms. Okay, so you can use it either to increase the voltage or to decrease the voltage. If you use number of terms less than n1, you'll decrease it. If you use n2 greater than n1, you'll increase the voltage. So the voltage that comes from the wall outlet is 120 volts. But if you get a device that takes 10 volts, you have to use transformers, right? And you can just simply adjust it by adjusting the number of terms, all right? So step-up transformer increases voltage. This one is used to increase voltage, okay? And step-down transformer is used to decrease voltage, okay? So that's how transformer works. The ratio, by controlling the number of turns of the primary and secondary, you can control how much voltage you get out of the output. All right, that's it for today. Do you have any questions? Well, you don't have any questions, so I'm going to see you on Tuesday. All right, we're going to work on a worksheet on this one.
Thank you,
All right.
Professor.
See you. Bye-bye.